In this video, we're going to be discussing the 5.4 and 5.5 material that has to do with applications of linear systems. Really just a fancy way of saying we're going to be looking at 2 sections worth of story problems that have to do with systems of linear equations. So the 5.1, 5.2, and 5.3 is going to be applicable here as we go through and solve different story problems. So some equations that I think are worth knowing are the ones listed right here. We have a total cost equation, which is the total cost is equal to a variable cost of some sort, plus a fixed cost, normally like a fixed income or a salary or something like that. We see this most commonly when we have commission problems or someone who works an hourly wage, something along those lines. We have our distance equals rate times time problem, which is also referred to as the D equals RT or DIRT equation, as some people like to call it. I think DIRT's a fun way of remembering that. Then we also have our mixture problems or bucket problems. This is the ones where I use buckets showing up quite a bit with this. A lot of this is review and material we covered in chapter 3, but we're just seeing it now with some new strategies to go through and solve these. And mixture problems follow using a process of having a rate of concentration of something, generally a percent of something, or a value of something, times an amount of a mixture or an amount of something else. This could be the value of some number of tickets sold. It could be the percent of water in a mixture of different drinks put together, something along these lines. We then have a much more generalized version of the distance equals rate times time problem, and this is referred to as the rate principle. And it says an amount of something is equal to some rate of something happening times a base amount, which is generally used as a time frame. So this can sometimes be seen as work equals rate times time, the amount of, maybe this is how many gallons of water have been siphoned out of a boat or something, or how many logs have been moved from one part of the forest to another for a forestry thing, something along those lines. But the rate principle is the most generalized version of the distance equals rate times time problem. It follows the same idea, but it generalizes and can be used to use in a lot more varying scenarios. And our last one that we have is a GPA problem. If we're going through and determining our grade point average for a class or amongst a certain number of classes that we are taking. This is probably the outlier of all of these in that it doesn't always create a system of linear equations, though it can in some instances. So a way of solving for the GPA is we are going to have the sum of the grade points. That's using the grade that was received and the weight of that specific class, a 1 credit class, 5 credit class, 10 credit class, etc. And then we're going to divide that by the total number of credit hours. I have this many 5 credit classes, this many 3 credit classes, and so on, all adding up. So we have this other way of writing it out using this fancy looking E that we have here. This is the Greek letter sigma. It's for adding things up. So adding up all the grade points divided by adding up all of the credits, and then we get the final GPA at the very end. Now the strategy that we are going to use for a lot of these is very similar to what we've seen previously in the chapter 3 material. Again, there is not really a direct, this is always how you solve story problems, this is always how you go through and solve these things, but I do want to note that there are some universal things that seem to show up with story problems, and we're just reiterating those here. So reading and rereading the problems as much as you need to throughout a whole process, go for it, do that. A lot of people will just read something once, call it quits, and then just start doing math at random or just give up entirely, and that's not what we want to do. Make sure that we're identifying useful information, labeling it, labeling variables, labeling numbers, and then really define what we are solving for. Half the issues that I've seen with students is that they will read a problem and start solving for thing A, but the problem is asking you to solve for thing B. So we correctly solved for A, but we're not even asked to do that in the overall problem, so we've gotten the wrong answer because of that. I do think it can also be worthwhile to make a sketch or a picture or something to create a visual of the problem, or just something to organize the problem with. That could be a table, as we'll see with some of our other problems we've used in the past, so a table could work there. And then create and adjust some equations as necessary. Bring in an equation, modify it a little bit, adjust it a little bit more, adjust it a little bit more, and then hey, we finally got the equation or equations that we need, and then we can finally solve that thing. Last but not least, make sure that you are checking to see if your answer is reasonable. For instance, let's say we had a mixture problem and we're mixing two things together. Does it make sense if I'm getting to a final answer that has one of them is positive and the other is negative? Does it make sense to have a negative amount of a liquid being added in with something else? No, it doesn't. So that would be our cue of, hey, something went wrong, I need to go back and double check my answer, my work, something along those lines in the problem. So we're going to take a look at 4 example problems that use a fair amount of these. A lot of these are probably going to look a little familiar back from the Chapter 3 material, but we're going to solve them using what we've learned here in Chapter 5. Looking at our first problem, we are told that Dr. Cox orders a dosage of 40 milliliters of a 16% saline solution for a patient. Since JD doesn't know how to do his job well yet, he panics and grabs a bag of 20% saline and another with 4% saline, not knowing what to do with them. In a fit of rage, Dr. Cox fumes off to solve the problem for himself. How much of the 20% saline and 4% saline does Dr. Cox need to mix to get the correct dosage for the patient? So we have some buzzwords that are showing up here for us, specifically that we need to mix some things together. So this is a mixture problem, and I'm specifically working with percentages of things in here, so that means I'm going to make the buckets and use that to organize how I'm going through this problem. Again, this is just for me what I have found to be the most useful, an organized way of going through these mixture problems. You can use a table, or you can use something else if you would like to, but for me the buckets work best. Now again, using the buckets, we always need to have the result at the very end, or outcome, or something along those lines for your labeling of the last one. Now we have 2 other solutions that are mixing together here. We want to label those at the top. I'm just going to call it solution A and solution B here. And then we need to label the amount of what inside here, and then a percentage down below. So I'm going to list the amount off to the side. We want to make sure that we're also specifying what unit am I tracking for an amount. Is it gallons? Is it liters? Is it pints? Is it cups? And we look to the problem to see, do I have any units that I have to associate with that? Well, I've been told 40 milliliters, so that's the unit for amounts that I'm going to be using in this problem. We'll go ahead and adjust that labeling right there. And now I have the concentration right down here. This is the part that again gets people into a lot of trouble. We can, for this class, we can only track one single type of percent in this entire problem. So this problem could give us 3, 4, 5 different percentages, and percent of water, percent of alcohol, percent of saline, percent of root beer, percent of orange juice, whatever it is. We can and will only track one of those. And I think finding the end result right up here tells us exactly what we need to be tracking for in the whole problem. I'm tracking percent saline. So I'm going to make that little note to myself down here. I'm just going to put that as percent saline. Perfect. So any other percentages that show up in this problem that isn't percent saline, I'm going to ignore. We are not going to be solving with, and it's completely irrelevant to what we're doing here. Now, how much of solution A, how much of solution B, and how much is my result going to be. We can start filling in some blanks here. I think the amounts are arguably the most straightforward ones that we can plug in. Well, we're told the result is going to be 40 milliliters. Let's plug that in. And I don't know how much of A and I don't know how much of B at this time. So I can leave those as X and Y or M and N. I'm going to choose A and B only because I'm going to keep the variables consistent with how I've labeled them at the top here. Now what am I doing in working with the concentrations? I need these filled in as well. So my result is going to have to be 16% saline. That's given to us at the very beginning of the problem. Solution A, which of these two different ones is that going to be? Doesn't really matter. We're just going to put the 20% there first, only because that comes first in the sentence. That's the level of choosing that we're working with here. Doesn't matter which one goes where, we just need to assign it accordingly. The 4%, that's going to go with B. We can just write that in. Perfect. Now that we have this set up for ourselves, we can go through and start creating some equations. Remember that if we are making equations out of this, we need to convert all percentages into decimals. So I'm going to go through and convert 20% into 0.2, 4% into 0.04, and 16% into 0.16. And now, making our actual equations here, we have two really nice ways of figuring those out when we have percentage and mixture problems like this. The amounts will always add together to equal the result. That's why we like to write them in this form. A plus B equals 40. So right there is our first equation. 40 milliliters, or I should say, A milliliters plus B milliliters is going to be a combined total of 40 milliliters. That seems reasonable there. Our second equation, because we have percentages, is going to be the amount of A times its concentration plus the amount of B times its concentration. And for the resulting one, because I am working with a percent problem, it will also be the amount of the result times the concentration. And we can write that in right here. And now I have my system of equations, and I can go through and solve this thing using the elimination method or the substitution method. It does not specify anywhere in the problem which method we need to use, so it's 100% our choice on what we want to pick and go forward with the problem. Me personally, I'm going to go ahead and use the substitution method here. I'm going to rewrite my first equation and solve it for, I'm going to solve it for A, so get A all by itself. That means this thing is going to get rewritten into A equals 40 minus B. And I'm going to substitute that into my second equation, and I'm going to write that new equation right down here, and I'm going to go ahead and solve that thing for B. And now that I've solved for and found my B value, which is the amount of solution B that I have, I can use that to find the amount of solution A that I have. Let's go ahead and work through that right over here. So now that I have the amount of solution A and I have the amount of solution B, generally good practice to somewhere nearby write out for ourselves solution A is 30 milliliters, and that solution B is going to be 10 milliliters. And there I have my final answer for problem 1. And again, we worked through this using the substitution method to get to our final answer, but you could absolutely go through this using the elimination method and you'd get to the exact same result. Either one would work. In our second example, we are told Michael, Franklin, and Trevor are attempting to get away from a local motorcycle club. They decide to lose the motorcycle club members by taking 2 boats from the same dock and splitting up along a river. Michael and Franklin take 1 boat and go up the river, and Trevor takes the other boat and goes down the river. The 2 boats have identical top speeds in still water. After 3 hours traveling at the boat's top speed, Michael and Franklin are 8 miles up the river, and Trevor is 24 miles down the river. Determine the speed of each boat in still water and the speed of the river's current. So there's a lot going on with this problem, and I don't think it's obvious where to begin with it. If nothing else, maybe we're able to see, hey, this sounds like I've got a time showing up and I've got some distances, but I've got weird things going on with speeds and rates and whatnot. So at the very best, this is probably a dirt problem, distance equals rate times time. But how we get something formulated from there, well, maybe we draw a picture and see what that looks like. So let's go with the idea here. Here we have our dock, because they're both starting there. And we'll see if we can get slightly artistic with this, see how well I can channel my inner Bob Ross for this video. So we've got our river here. You know, if you want to put a shark or something in there, because you're frustrated with the math and you need a shark for the day, yeah, hey, why not? So we want to determine from that dock which way the river's current is going. It doesn't sound like it really matters which way we label it, but the river's going to have a consistent current. So we'll just put something like this. The current is traveling in that direction there. So it's going from left to right on our screen. Okay, makes sense. Now, we have, from the dock, it looks like we have Michael and Franklin. They are going up the river. So we have some of them. Let's see if we'll use red here. So from the dock, we have Michael and Franklin that are traveling up the river. We'll just do N, and F. So Michael and Franklin, they're going up the river. And then we are told that Trevor is going down the river. So we'll do his in green. So they're starting at the same spot, and he's going down the river. And he's traveled much farther. Okay, so this gives us a bit of a visual of what's going on with this, and we can maybe start to see and formulate how the speeds of the boats correspond with this current that we have. If Michael and Franklin are going up the river, the current is working against them, so that means that they're probably going to be going slower than what the boat's top speed actually is. In contrast to that, Trevor's going down the river. He's going with the current, which means that the current is probably adding to his speed, making him go faster. And that would also explain why we have such big differences in the miles and distances that they've each traveled. So let's keep that in mind and go ahead and make a little table for ourselves to see how we could map this thing out. So I'm going to scroll us down here. We're going to use our dirt table again. Bringing it back from, I believe this was one of the chapter 3 problems, or sections. So we have distance, we have rate, and we have time. The distance is in miles, the rate is in miles per hour, and the time is in hours. Now we have 2 sets of data here. We have information about Michael and Franklin, so I'm just going to keep doing M and F here just for shorthand. And then we have Trevor, some information there. And then again, as we've done in the past, maybe we're going to have a total that's going to be showing up here in these bottom rows, but if it happens, it happens. If it doesn't, it doesn't. That's fine. So let's start filling in some information in our top 6 boxes that we have here, because we need all of these filled in. Do I know distances, rates, or times for either of these? Well, for scrolling back up, we're told Michael and Franklin are 8 miles up the river, and Trevor is 24 miles down the river. So we can fill those in accordingly. Michael and Franklin are at 8, Trevor is at 32. Whoops, 24, sorry. Wrong numbers there. I'm adding things together and I don't need to be. Okay, do I know anything about rates or times after 3 hours traveling at the boat's top speed? Okay, so that tells us that they both traveled for 3 hours. We are also told in the problem, I think it was somewhere up here. Yeah, they split up along the river, so they're leaving at the same time. Okay, so that means that they're both traveling for 3 hours worth of time. Maybe they left at different times, but we're told that they travel at 3 hours, so that's a reasonable assumption there. Now we have to figure out the rates. So we are told that the boats have the same, or the identical top speeds in still water. So whatever that speed is, we could write that down maybe as just a random R in here. So they would have a top speed of some kind, the boat's top speed. However, with the current coming into play, remember, Michael and Franklin are going upstream. They're going against the current. So that means whatever the boat's top speed is being subtracted by the current speed. And in contrast to that, Trevor is going downstream. He's going with the current, which means that the current would be adding to his overall speed there. I've not been told or asked anything about a total distance traveled, a total speed, or a total time, so we can just kind of cross those out as ones that we aren't going to be using for this problem. And that's fine. That does still show up with these problems. We just list that row in there in case it's going to show up. And now I can look at this problem and say, let's make some equations out of this, just like we did in the past. So we'll write those in right here. And here we have our system of equations. We have two equations, each of which have two unknowns in them. I could rewrite them a little bit further if I wanted to. Let's say I distribute the 3 through to everything. I'm going to go ahead and write that result right over here. So I'd be getting 8 equals 3r minus 3c. And then 24 equals 3r plus 3c. And again, all I'm doing is just distributing these 3's through accordingly. Now I have a system of equations, and I can go through and solve this thing using any method that I want. I'm going to go through this and solve it out for r and c using the elimination method, because I'm noting that the c values have additive inverse coefficients in front of them. One is a -3, one is a +3, so that sets it up really, really nice to use the elimination method here. But again, you could use the substitution method if you wanted to as you go through it. Let's go ahead and solve this thing out for our answer now. So now that we have the top speed of the boat, we have the current speed, we can go ahead and write that over here, just kind of summarizing it all here. So we have the boat's top speed is approximately 5.33 miles per hour, and the current has a speed of approximately 2.67 miles per hour. Now, generally speaking, with a lot of these, we don't get as gross decimals showing up as these, but I think it's worth seeing that it can still show up from time to time here, and we can still work with that all the same. Hopefully, if you went through and solved this using the substitution method, you got a very similar answer to this, or the exact same thing. But this is everything and how we go through and solve example 2. For our third example, We are told Jeff and Ryan are building a new stone castle in Minecraft together. Because it's going to be massive, they determine they need to take 2 days to assemble all the blocks of stone that they need. On the first day, they put in 4 hours of work each and collected a combined 2,500 blocks of stone, I should say. On the second day, Jeff worked for only 3 hours and Ryan worked for 5 for a combined total of 2,805 blocks. I'm looking at my numbers wrong. Of stone gathered. Determine how many bricks per hour Jeff and Ryan are individually able to gather. So what we're going to be using here is the modified and more generalized DIRT equation here. And it's this amount equals rate times base. And this base in this instance is going to be the time. So an amount of something based on some rate that, call it work, is being done, multiplied by some base amount, which is going to be time, or hours in this instance. Now with this problem, I think similar to the DIRT problem, we have three sets of data here. We have 2 days that they're working, and we have information about Jeff's and Ryan's working hours and rates each of those days. So what we're going to try and do here, and this is just to show another way that you can organize this. You can use it, you can modify it, you can say this makes no sense. I'm going to go back to the table method if you want to. Let's look at each day individually. So we have day 1. What was the amount that they both assembled? Okay, we were told that the first day they collected a combined total of 2,500 stones. Let's go ahead and write that in. Now that's the combined amount that they both had together. We know that this is equal to, let's call it Jeff's amount, because we don't know how much he gathered, but Jeff gathered some amount of stuff, plus Ryan's amount. We know Ryan gathered some amount of stone as well. So we have our very generalized setup here with this. Do I have any more specific information about the amount of stone that Jeff collected? Well, we are told that he did work for 4 hours. That could be the base here, but I don't know the rate that he gathered stone at. Turns out that that's actually what we're solving for. So I can slightly modify my overall equation, make it a little bit more specific. I can say that of the 2,500 that was gathered, Jeff's amount was some rate, and I'm just going to label that as G for Jeff, and he worked for 4 hours that day. So Jeff's rate times 4 hours of work. Similarly, we don't know Ryan's rate, but we know that he also worked for 4 hours, so I'm going to have Ryan's rate, R, times the amount of hours he worked for. And this is the best that I can do with my first day of information. It also is one of the 2 equations that we need. Let's go ahead and write next to it, write in day 2 here. Let's see what we can determine from this. So we're told with day 2, on the second day, Jeff worked for only 3 hours and Ryan worked for 5 for a combined total of 2,805 blocks of stone gathered. Hey, there's my total there. So we can rewrite that in here. This is 2,805. And again, we have Jeff's amount. And then we have Ryan's amount. And whatever those individual ones are, we are going to combine those together. But here we have some slightly different information. On the second day, Jeff worked for only 3 hours. So we can safely assume that his bricks per hour, the rate that he's working at, is going to stay the same. But the hours that he worked is going to be lower than it was on day 1. So I can modify this second equation as such. So Jeff's amount, he has still some rate that he's working at, which we don't know, but he only worked for 3 hours. We can look at Ryan's amount, and again, we are going to reasonably assume with this problem that he's working at the same rate, but he worked for 5 hours instead. So the amount that Ryan got plus the amount that Jeff got in the second day yielded this brand new total of 2,805. Let's go ahead and bring these together as a system of equations now. Which one's on top, which one's on bottom doesn't matter. We see that we have a new system of equations emerging. And once we have this system written out, it is now our choice on what we would like to do to go through and solve this thing. We can use the substitution method, we could use the elimination method. Doesn't matter which one we'd like to use, we just need to pick one and then commit to it. I'm going to use the elimination method because why not? I'm going to go ahead and with this system, I'm going to go ahead and multiply the first equation by something, second equation by something. I'm going to work to eliminate the g's here. So what's the lowest common multiple between 4 and 3? I think it's going to be 12. So I'm going to multiply the first equation by, we'll make this one the negative. Multiply it by -3. I'm going to multiply the bottom one by +4. And I'm going to go through and do the rest of the elimination method. Write down here, solve for g, and then solve for r. Well, actually, solve for r, and then I'll solve for g. But get to our final answers right down here. And from here, we're getting to our final answers of Jeff working at a rate of 160 blocks of stone per hour, and Ryan working at a rate of 465 blocks of stone per hour. As with the previous problems, you are welcome to use the other algebraic method than the one I used. Again, I used the elimination method here, but you can absolutely go through and use substitution to get to your final answer. It should be the exact same as well. And again, we have a slightly alternate method for setting this thing up and making sense of it for ourselves. You're welcome to use this. You can modify it, do whatever you need to with it. We should be getting to our final answer right here. For our fourth and final example, we are told that the first semester Morty is enrolled at GRC. He earned the following grades: C in a 3-credit English class, A in a 4-credit science class, B in a 3-credit speech class, and a C in a 4-credit psychology class. Rick thinks Morty should drop out of college to join him on interdimensional adventures instead. Pretty standard issue stuff right there. And we're assuming that an A is a 4.0, B is a 3.0, C is a 2.0, D is 1 point, F is 0 points. Grade point averages, or GPAs, generally they assign point values to these, and this is the one that we are going to be using for this particular problem. It should be noted that different problems in different colleges use different scalings and point values depending on how they've decided to work with those, so just be on the lookout for that compared to this example here. These are numbers that I just came up with. They will vary depending on the school or class that you're looking at. So we have two parts to this that we're going to go through. We want to first determine Morty's GPA for his first semester. We then want to see, well, Morty wants to raise his GPA to a 3.0. Maybe it's a little bit of a hint at where his GPA is in the first semester. How many credits with a grade of an A must Morty take to meet his goal? So we have two parts to this, and we'll go through them each individually here. So let's start with part A. We are told to determine Morty's GPA for his first semester. So the way we are going to do that is we are going to add up the total credits that he's earned with the weight that each credit or each class has. So for instance, a 3 credit class versus a 4 credit class versus a 3 versus a 4. Maybe we have a 2 credit class or a 1 credit class, something along those lines, but that is going to play into how we set this up. So the way we have these is we say, what was the grade that he earned in his first class? That was a C. A C is worth 2 points, so that means for his first class he had 2 points, and the weight of those was a 3 credit class, so we can multiply that by the weight of 3. He also had a 4 credit science class at an A, so that means he has 4 points out of 4. I need some extra space here. Then he had a B, so that's 3 credits at 3. And then lastly, he had a C and a 4 credit psych class, so a C is 2 points at 4 credits. Okay? So there we have each of his class grades in the front, and then the credits attached to them on the back side, but they're all going to be multiplying together for each individual class. Now at the bottom, we are adding the grade hours that he had with those classes. And grade hours are just the number of credits that each class is worth. So that's going to be 3 plus 4 plus 3 plus 4 down below. All of this information in the problem that we're seeing here, and very similarly with your problems, must be given to you. We don't have any way of just guessing at these things and just saying, oh, I'm just going to randomly give it this number of credits or that number of credits, because if we do that, we're going to get wrong answers. And now we have our entire setup, and this total, once we've simplified the numerator and simplified the denominator, is going to give us our GPA. So we'll go ahead and solve that now, and I'm going to be using a calculator off screen to get to that answer, and we'll see what his final GPA is. And we have for the first part here that Morty has a GPA currently of 2.8. We're going to round it to 1 decimal place because most GPAs end up going only out to 1 decimal place is all. So really I got 2.78571 for a bunch of extra stuff, and we're just going to round it to 1 decimal place here. Now for part B, we are told Morty wants to raise his GPA to a 3.0. How many credits with a grade of an A must Morty take to meet his goal? So we have 2 routes that we can take here with this. I'm going to put part B right down below. Whoops, don't want to highlight. We're going to separate this out. Let's go ahead and take a look at this, or think on it. So what we have is the number of credits and everything that he's done up till now. What I'm then going to be doing is I'm tacking on an additional number of credits at a grade of an A. So I have 2 ways that I can go about doing this. I can rewrite this whole thing down below here, and I can add on the little bit of extra stuff at the end, up top and down below, which there's nothing wrong with that, but we look at this and see that this is kind of a mess of stuff and kind of a mess of stuff here. Or I can simplify down to noting he has a 2.8 with 14 credits. And I can say if I'm adding all of his material and his grades together, he has a GPA of 2.8, and the weight of that is a weight of 14 credits. Make that 0.8 a little bit better. There we go. Now we are asked how many credits within A must Morty take to earn his goal, or to meet his goal. So I'm going to add on a grade of 4, but I don't know how many credits he's going to have. So I'm going to put an X in here. So he has 14 credits at a 2.8 plus some number of credits at a 4.0. I need to make the denominator, and again, that is going to be the number of credits adding together. That's going to be 14 plus X. And then what do we want his resulting GPA to be at the very end here? We're told he wants to raise his grade to a 3.0. So I'm going to write in 3 over here for his resulting GPA. And suddenly, I now have an equation that I can solve. I have a fraction equals technically a fraction on this side. This 3 is implied to be over 1, that invisible 1 hanging out down below there. So I can actually do cross multiplication, thinking back to our 8.7 material, to help me get to my answer here. So I would have 2.8 times 14 plus 4 times x is equal to 3 times the entire denominator, 14 plus x here. And now I can go through and solve this equation out for x. And we get to our final answer here of 2.8 credits. Now, as a warning to everyone who's watching this, this is something that a lot of these problems do that kind of makes them a bit tricky. If we are looking for the pure mathematical answer, it's going to be 2.8. However, in the context of the problem, we're asked how many credits with a grade of an A must he earn. I don't think we have, or at least I have not ever seen a class where we get a 0.8 credit load in there. So if we can't have decimals or parts of a credit or full credit as an answer here with this, we need to determine what is the nearest full credit amount that would work with this. So what's the nearest amount this is going to be? Well, if he needs a 2.8, I could not round it down to a 2 because that's beneath what he needs. However, if he did get and take 3 credits, that is going to be the correct final answer because we can only have full credit amounts. We can't have decimal amounts with most problems here. So be on the lookout if you get problems like this for decimal credits, and making sure that we are kind of doing a weird take on it, but almost always rounding up. If I have something point something else, always round up to the next whole number if we're asked about full credit amounts, especially with problems that are asking us stuff like we have here in part B. It's kind of a tricky part that shows up with these problems, but it is worth noting, at least putting on your radar, to be on the lookout for that at the very end. As a recap of the material that we covered today, we were working with applications of linear systems, or applications or story problems of systems of linear equations. We had our main equations that generally show up in this section listed right here, and we had a quick review on our strategies on how we could go through and solve these things. An immense amount of the material that we used and the thought processes that we had in the Chapter 3 problems are showing up here again, but now we have 2 new algebraic methods to solve them, the 5.2 substitution method and the 5.3 elimination method. If a question does not specify which method that they are asking you to use to solve this particular problem that you're working with, you can go ahead and use whatever method you would like. If you are in my class and you are watching this video, please note that on each question, I will be noting, hey, I want you to solve it using this method, or I will note, I want you to solve it using that method. And if I don't state any particular method in the directions, then you are free to use whichever method you would like, which is what I tend to use and allow for a lot of story problems. We then went through and looked at a mixture problem. Again, coming back from the, I believe it's the 3.3 material, just making its return back here. Yeah, 3.3. We had our distance, rate, time problem showing up. That was from the 3.5 material making its return. Our third problem was a variation on the distance, rate, time problems. It's working with work and amounts in total there. And then our last example here had two parts working with GPA and how we calculate those, which is kind of a new one for this section. Hopefully everyone noted with number 4, we never actually used the substitution method or the elimination method to solve this. That is correct. A fair amount of these GPA problems don't really lend themselves to either the substitution or elimination method, but the method that we went through and the process that we used in this example is generally what we use with solving a lot of them out. And then lastly, make sure that we're double checking for how many credits. Make sure that most of these problems we're rounding up always to the nearest whole credit. If a problem states otherwise, then you can leave it as a decimal, but most of these require us to round up accordingly to get to our correct final answer. But that's everything for the 5.4 and the 5.5 material.